So in the previous videos, we've done acid additions to alkenes, halogen addition to alkenes, oxymercuration, demercuration, hydroboration, oxidation, hydrogenation, dihydroxylation, epoxidation. Oh man, I'm starting to feel like I'm swimming in a sea of silliness. Yeah, we've covered a lot and we've covered it quickly, but it's not time to stop yet. We're talking about this reaction next because this is also an oxidation reaction. It's not a syn addition oxidation, but let's talk about what it does do. So oxidative cleavage of alkenes. We're going to cut an alkene. It's called ozonolysis. This little lysis part, maybe you've heard that in your biology classes. Lysis is cutting. Cutting with ozone. This is ozone. Ozone has this sort of Lewis structure. O's. Three of them all connect together, double bond between one of them, single bond between the other. Yes, it has resonance. The pi bond can attack that carbon, that's an oxygen. The pi bond can attack that oxygen over there, give electrons to that middle oxygen that will relieve his positive charge, but at the same time, let's let this terminal oxygen attack that carbon. Why did we attack that carbon? Because the nucleophile always attacks the more substituted, the better carbocation character side. The better carbocation character side. Okay, so I end up with this. This always reminds me of a little alien. Anybody with me on that? A little alien on Toy Story? Yeah. This little alien, not super stable. We've got not one, but two peroxide bonds, two OO single bonds. Uh-oh, that's not good. Let's not hang around as something like that. So this thing decomposes. Let's break this thing down. Oh, I didn't really mean to say green. Well, let's do it like that. Green, aliens are green anyway. So we end up making a double bonded oxygen. That becomes doubly bonded, but that oxygen is still connected to this singly bonded oxygen, like that. Positive on this oxygen. I wish I had sat this a little different direction, but oh well. This is my other piece. That carbon-carbon double bond folds up to make a pi bond between that oxygen-oxygen, and we broke that oxygen-oxygen single in the process. This is weird. These aren't real stable either, so let's do some more. Actually, no, I'm going to erase this and sit it a different direction. I'm sorry, I'm not backing up, but I'm going to erase this and sit it a different direction so that my next arrows are a little more understandable, I think. Okay, so I tried to not change it too much so that it's not too confusing, but this thing, not super stable, so another little reaction happens. Like this, and you say, this is crazy mess that you're doing right here. I agree, this is crazy mess that we're doing right here. When you hook up those things, you get this. Oops. So you've got an OO single bond still, not great, peroxide bonds are not stable, but this ring is much more stable than that alien was. That ring is stable enough to even have a name. That's called an ozonide. This green thing is the ozonide. Those are identical, the black thing and the green thing. Okay, ozonolysis, oxidative cleavage of alkenes. Ozonolysis usually takes place at negative 78 degrees Celsius. That's a pretty cold temperature. It's a very specific temperature as well. Not to get too far off track here, but the reason we say negative 78 is if you dissolve dry ice in acetone, the temperature that equilibrates to is negative 78 degrees Celsius. So anytime you see this very specific negative 78 Celsius, that's dry ice in acetone. This whole reaction is ran in a bath, a cold bath of dry ice acetone. Okay. So the reason that I even point that out when we avoid that kind of thing a lot of the times, the reason I even point that out is to say, this was crazy mess that was happening. This was a little bit crazy mess. This was a little bit crazy. Yeah, this ozonide is not stable, but it's stable enough to exist at negative 78. Higher than that, not so much. So these are a little bit bizarro arrows, but we can justify at our level of organic, we can sort of justify and say, meh, it's real cold temperature. You can do some little bit weird stuff at real cold temperature. That's not exactly acceptable, but it's what we're going to say anyway, and maybe you'll accept it. So all of those arrows was to get me to the ozonide. But what happens to the ozonide? You can't just have an ozonide sitting around on its own. It's not stable enough to do that. So if I have an ozonide, I can treat it with one of two things, one of two types of reagents. If I treat it with this type of reagent, that type of reagent is called reductive workup. Or I can treat it with this type of reagent, and that type of reagent is called oxidative workup. So reductive and oxidative workup, that tells you what happens to your ozonide after you do the ozonolysis. So this is oxidative cleavage. The net result is you're going to be oxidized. Your starting material becomes oxidized regardless of whether you did reductive workup or oxidative workup. So sometimes that confuses students, and I'm just trying to steer you the right direction. Ozonolysis is an oxidation reaction. This product becomes oxidized when you do ozonolysis regardless of whether it's reductive or oxidative. Okay, then what's the actual difference in reductive and oxidative? This zinc and water, and actually another reductive workup is dimethyl sulfide, Me2S. Zinc and water, or dimethyl sulfide, reductive workup conditions leads to potentially aldehydes and ketones as your functional groups that you make. Hold that thought. Oxidative workup leads to potentially ketones and carboxylic acids. Do we have to know this mechanism of ozonolysis, this past mechanism? No. Or how these oxidative and reductive things work? No. We don't have to follow along and understand these mechanisms, but we do need to know how to predict the products of these reactions. One thing before I talk about predicting the products, the little note that's behind my scribble there says equivalent to hot refluxing KMNO4. We'll talk about that in a minute. Remind me. Okay. The take-home message. In order to predict products of ozonolysis, you need to know if it's ozonolysis with oxidative or ozonolysis with reductive workup. This one is reductive. This one is oxidative. Going to be, I'm just writing slowly. The net result is you karate chop that alkene. Chop it in half. Squeeze a little oxygen between where you cut, oops, that's the wrong direction. Squeeze a little oxygen between where you cut the double bond. So you cut the double bond, squeeze an oxygen on both sides. Okay, I can do that. Squeeze an oxygen on both sides where you cut those carbons. So far, my products are identical. My top products and bottom products are identical. I've got 4 carbons over here, 4 carbons over here, 2 carbons over there, 2 carbons over there. I haven't lost any carbons. That's important. Don't lose any carbons. I ended up chopping my molecule in half. Okay. Reductive workup, you're finished. You squeeze oxygens between where you cut the double bonds, and it's finished. Nope, this is supposed to be H2O2, H2O2. Oxidative workup, you go back and ask yourself, after I chopped this thing and squeezed in an oxygen, do I have an sp2 carbon that has a hydrogen on it? This sp2 carbon has 2 carbon groups on it. So it's done. It doesn't need any more work. This sp2 carbon has a carbon and a hydrogen. Because that has a hydrogen, this oxidative workup causes further reaction. I got quotes in the air over here. Further reaction. And that further reaction causes further oxidation to yield this compound on the right. This is a carboxylic acid. With reductive, it's an aldehyde. With oxidative, it's a carboxylic acid. Okay, So students sometimes say, all right, ozonolysis always makes ketones and aldehydes or ketones and carboxylic acids. Not necessarily true. It depends on the structure of your alkenes that you begin with. Let me give you a couple more examples. So if I have an alkene that looks like this, super simple alkene. Well, let's do ozonolysis. You'll see textbooks write at -78, but I am often a little too lazy for that. Let's do one with reductive workup. Let's do one with oxidative workup. Let's do ozonolysis with this bottom one. Reductive workup, we're just going to write an RW. We're going to write an RW for reductive workup, and you're going to follow along and be okay with that, I hope. We're going to write an OW for oxidative workup. Okay. I'm going to start by chopping my alkene in half. Chop. I'm going to go in and squeeze 2 oxygens where I cut my alkene. Squeeze 2 oxygens where I cut my alkene. Squeeze 2 oxygens. Actually, that left half is the exact same as the example we just went through, and I just realized. Squeeze 2 oxygens between where I cut my alkene. And then I go back and analyze. This sp2 carbon, where I cut that alkene, does this sp2 carbon have any hydrogens? Nope. 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 So for this top example, my products are identical. Whether I did oxidative or reductive workup, I made all ketones. It's actually the same molecule, acetone. I made all ketones in that top example. Okay. Do I have any hydrogens connected to this sp2 carbon? Nope. Do I have any hydrogens connected to this sp2 carbon? Yes. So then I go back and look. Oh, it's reductive workup. No further work needed. No hydrogens. Yes, there's a hydrogen. It's oxidative workup. Ooh, I need to add an extra oxygen. Extra oxygen. Oh, I didn't realize that's still orange. Extra oxygen. So in this bottom example, I do get different products depending on whether it's oxidative or reductive. Sometimes you get all ketones, like the top example. Sometimes you might get all aldehydes or all carboxylic acids. It depends on what groups are on your alkene to begin with. Okay, one more thing before we move along to the next thing. When you have multiple alkenes within a molecule, ozonolysis cannot control itself. It cannot help itself. It's going to chop all of the alkenes within that molecule. It just can't help it otherwise. Okay. So ozonolysis, this says, is useful in structure determination. What the heck does that even mean? Why, I don't know. If I have an alkene and I know that it's an alkene, maybe I've done some sort of qual test to confirm that it's an alkene. I know that it has an alkene, but I don't know where that alkene is. I can subject that alkene to ozonolysis, analyze the pieces that I get out of ozonolysis, and deduce the structure of the original unknown alkene. Okay, the truth is, new technologies, it's not really that new, you guys are young, I know, but new technologies like NMR spectroscopy, carbon, proton, NMR, IR has been around for a really long time. Another spectroscopy we've not talked about, mass spectrometry. A lot of spectroscopies exist now that a scientist would probably choose those other methods of structure determination, but ozonolysis is still a way that you can determine structures of unknown compounds based on analyzing the pieces that you get. So let's walk through a couple of examples of structure determination using ozonolysis. All right. An 8-carbon alkene gave only the following degradation products upon ozonolysis with reductive workup. What is the structure of the alkene? Okay, my first thing to point out is it gave only this product. This product has 4 carbons, and I started with an 8-carbon alkene. It must mean that I ended up producing 2 of the very same alkene, 2 of the very same aldehyde, 2 of the very same aldehyde when I chopped my alkene. Actually, just like this previous top example back here, I ended up producing 2 identical ketones, because I chopped a symmetric alkene. So what I'm saying down here is this must have used to have been a symmetric alkene. So imagine those O's weren't there, and those carbons that the O's are connected to used to be stitched together. So I'm going to say, imagine this was my alkene that I started with. That seems legit. If I chopped that thing, yeah, I would make that product. The unfortunate news is if I chopped this product, I would also make, if I chopped this reactant, I would also make that product. So ozonolysis is useful to help determine the structure, but it does not tell you about the stereochemistry. This is the E alkene. This is the Z alkene. Ozonolysis doesn't tell me what it used to be before you chopped it. So it's either E for octene or Z for octene. Well, I couldn't get those words out very well. Ugh. Let's try another one. This one's a little bit tougher, but doable. I like zigs and zags, so I'm going to start by drawing this guy as a zigzag. 1, 2, 3, 4, 5. This guy. So this one says C8, H14. 1, 2, 3, 4, 5, 6, 7, 8. All right, that's good news. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, we've already got all of our C's and H's represented. So what used to have been connected was these oxygens got squeezed between my alkene. So this carbon and that carbon must have used to have been connected before I ozonolyzed it. I'm going to number these carbons just so that I can keep track of, whoops, that's an 8, keep track of things a bit better. Apparently this used to be a 7-membered ring, and you say, I'm just getting good at drawing cyclohexanes, and you throw a cycloheptane at me. Are you crazy? Yeah. Here's a cycloheptane. It doesn't matter where I start my numbering. I just started it at some arbitrary point up there. Carbon 1 and 7 are what I'm trying to connect together. So carbon 1 and 7 should have the alkene connecting them. 1 and 7. 7 should have carbon 8 hanging off of it. So apparently this was the molecule that I chopped in half and got that molecule out of it. Okay, one more example, and this is the end of ozonolysis. An unknown compound, which has the molecular formula C10H16, was found to decolorize bromine in carbon tetrachloride. What does that mean? Was found to decolorize bromine in carbon tetrachloride. That means red bromine disappeared when I added my compound that's unknown to it. Qual test positive, I've got an alkene. And gave a brown precipitate with cold dilute K-4. What does that mean? A second confirmation of my qual test. Alkene reacts with purple potassium permanganate to give you brown manganese 4 oxide. So further confirmation, I've got at least one alkene in this thing. When it reacted with hydrogen gas and palladium, it produced 1 isopropyl 4-methylcyclohexane. Oh, that dash should not be there. Whoops, pretend that dash is not there. Oh, that dash should not be there. That should be all together one word. Whoops. Ozonolysis followed by reductive workup yielded the compound below as one product. What is the unknown structure? Oh man, this has a lot of parts. Where to begin? I'm going to start, not that this is exactly where you should start, but I'm going to start with the DU of that compound, the degrees of unsaturation of that compound, because that's going to tell me how many alkenes I have, potentially. 2 times the number of carbons. Oh, that's a 10. Dang it. 2 times the number of carbons, plus 2. Plus nitrogen, minus hydrogen, minus halogen. Yeah, over 2. So it's 22 minus 16. We get a DU of 3. Okay, so that might mean I have 3 pi bonds. Hold your horses. When it reacted with hydrogen gas and palladium, that's hydrogenation, it produced 1 isopropyl 4-methylcyclohexane. So this is telling me kind of my framework of my compound, but I've got some double bonds, and I don't know where those are. So if I take a look over here at my DU, my product of hydrogenation tells me I have one ring. So DU minus one ring, that means I must have two pi bonds, two alkenes in this thing. Okay, I'm gathering my data, I'm getting my evidence together, I'm feeling confident. Where now? I go back over here and I count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Uh-oh. See 10, but I've only got 9 represented. Yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Uh-oh, I've got 14 hydrogens represented. So I'm missing 1 carbon and 2 hydrogens. I'm missing 1 carbon and 2 hydrogens. So it must mean I'm missing this little piece. So it says, ozonolysis with reductive workup yielded the compound below as one product. What they did not tell you is this product was excluded, because you can deduce that that product has to have been there. Yeah, okay. All right, so I'm going to go back to my compound over here and just give everybody numbers. I'm not giving them numbers with any significance. I'm just giving them numbers so that I can have some things to compare and consider. There are my 10 carbons. In order to, how do I say this? We need a 6-membered ring. So that means we need to find out which oxygens were stitched together, or we should stitch together, in order to make a 6-membered ring. If I try to stitch carbon 2 to carbon 7, does that make a 6-membered ring? Yes. If I try to stitch carbon 8 to carbon 7, does that make a 6-membered ring? No, it makes a 4-membered ring. If I try to stitch carbon 2 to carbon 8, does that make a 6-membered ring? No, it makes a 1, 2, 3, 4, 5-membered ring. So my first thing that I said was 2 must be stitched to 7. So I'm going to go in purple over here, and I'm going to say 2, 3, 4, 5, 6, 7. I'm going to make a bond between 2 and the 7. And if 2 and 7 is what I'm stitching, that means there's a pi bond that exists between carbon 2 and 7, because those had oxygens, and I'm taking the oxygens away. Okay, carbon 2 has a 1 on it. Carbon 5 has a carbon 8 on it. Carbon 8 has a carbon 9. Oh, that's a 9. Brain dead today. Carbon 8 has a carbon 9, and carbon 8 also has a carbonyl, and we also have a carbonyl, carbon 10. So can you see the prediction of what comes next? Carbon 8 and 10 must have been connected. So what I get here, rather than erasing, I'm going to actually add the pi bonds to this green structure. So I had a pi bond over here between 2 and 7. We'll go ahead and number these guys. And then 5 was connected to 8. 8 and 10 I'm now connecting. So the green thing in the middle is the compound that I subjected to ozonolysis and got this product and that product out of it. An ozonolysis problem can be kind of tricky, but I think you should be expecting at least one anyway. This compound down here is what's called a terpene. Terpenes are found in a lot of plants, leaves, trees, things like that, a lot of natural product kind of stuff. Kind of cool. There are a lot of different varieties of terpenes, and they all kind of differ based on where their alkenes are within their rings. So you can know that you have a terpene, but you might use ozonolysis to detect where those pi bonds in that terpene actually are. Kind of cool. We're going to call this video wrapped because that's all about ozonolysis. It's the final oxidation reaction we're going to talk about, and our next subject is pretty different from that. So done with this one, on to the next one.